Hi, so today we're going to be learning about how to deal with the parametrics. So first of all, let's look at a problem. The position of the object is moving on a curve xt, yt at the time t. So also we are given dx dt is root t over 2 plus t, and dy dt is cosine t squared minus 1. And we are also given at time equal 1, which the position s1 at time equal 1, which is x equal 2 and y equal 4. So now let's look into the first problem. So we are supposed to find a position, velocity, and the acceleration at time equals 3. So we can start with the easiest one, which will be the... Well, let's do this in order. So first of all, we want to find a position s time equals 3. So what we are going to do here will be the fundamental theorem of calculus. So basically, S3 will be equal to S1 plus integral 1 to 3 dx dt with respect to t, I mean x1, and y1 will be equal to, and y3 will be equal to y1 plus integral 1 to 3 dy dt with respect to t. And the rest will be the calculator work. So now let's take out your calculator. We turn this on. First of all, we want to make sure we are in the parametric mode instead of the function mode. So we're going to hit y equal. Now we're going to enter what's the dy dx and dy dt equation as we are given. Usually I like to leave the next one as a derivative, which saves us some time because we usually need to use it. But when do you need to do what, you have to interpret it by the context. So in this case, let's say x1t is root t divided by 2 plus t, which is basically our given dx dt, and let's type in our given dy dt here, which will be cosine t squared minus 1. Okay, so let's quit and math 9 integral so we want to figure out what's the areas under the curve from 1 to 3. So basically we go to VARS y curve number 2, because we're on parametric. We want to do x, and so from with respect to t, and we want to do it from 1 to 3. And this tells us the area under the curve from 1 to 3 on dx dt will be 1.394. And we know x1 is 2 from given information, so this will be 2 plus 1.394. And let's do the same thing for y. Basically, we just re-enter the whole equation, but we change the x1 to y1 instead. Let's see. So we know the area under the curve for y from 1 to 3 will be basically 0.28, because this is a so we round it up 0.281. We also know the at y1 at time equal 1 the y is 4. So here's what we have, and therefore we have y3 is equal to 2 plus 1.394, that's 3.94. I mean 3.394. And this is 4 plus 0.281, so 4.281. Okay. So now let's look into the velocity. So V3 is basically dx dt 3 and dy dt 3. And since we are given the equation about what's dx dt and dy dt, so let's get back to our calculator. Make sure we have the same equation. What we want to do, we just want to pull out a table, which is second graph, and that will give us a table. So since we know we want to find out what's the dx dt and dy dt at t equals 3, so we look at t equals 3, we know dx dt is at t equals 3 is 0.775. Let's round up the 4. Also, we know that dy dt time equals 3 is negative 0.14. Let's round up the 5 to 6. And here's what we have for the velocity. That's it. And also we want to figure out the acceleration. So the acceleration at time equals 3 will basically be d2x dt squared 3 and d2y dt squared 3. Notice we don't actually have to be able to differentiate it ourselves. We can let the calculator do all the work. So let's go back to the y equal. And look, that's why I always leave the differential equation here. In this case, we basically turn off the graph for here, and we turn on the graph for the differentiations. So we turn this on, and we can check the table again. And okay. Morning, Miss O'Neill. I'm doing a film. Oh, sorry. Okay. So basically, at time equals 3, the acceleration will be the acceleration for x will be 0.0516, and the acceleration for y will be negative 5.936. Okay, and I think that's what we need to have for the part A. It asks us for position, which we have velocity and acceleration at time equals 3. Okay, doke. So let's see what's the next part. Okay, so the next part wants us to find the speed of the object at time equals 3. In this case, we need to know the speed of object at time equals 3 is basically v3. That's what we use for speed. And equal to the square root of dx dt at time equals 3 squared plus dy dt at time equals 3 squared. Okay, so yeah, basically we know what's dx dt at time equals 3 and dy dt at time equals 3 from the previous problem. So we can write this into square root 0.775 square plus negative 0.146 square equal, so we will let the calculator do the work. .775, oops. squared plus parenthesis negative 0.146 squared. Da-dun. And we know the speed at time equals 3 is 0.78. Let's round it up to 9 since the next digit is 6. Okay. And that's our speed at velocity, sorry, at time equals 3. Okay. And the next step is find out the total distance traveled by the particle from T1 to T3. Notice that there is a difference between the total distance and the position or displacement. So what we are going to do here is we're going to have to integrate. Let's set up the equation. Total distance is equal to integral from the lower bound, which is time equal 1, upper bound to t equals 3, and root dx dt square plus dy dt square with respect to time. Okay, so this is basically another time we make the calculator to do the work for us. So here we integrate number 9 and square root. So notice previously we set up the xt equal the dx dt that give us and the y1t equal the dy dt that give us. So here's what we're going to do. We're going to type in vars y vars 2 x1t square plus vars y vars 2 parametric y1t, and we square. So notice when we square this here, it's basically like we're squaring the equation here. And we close the parenthesis. If we don't close it, there's going to be a problem when we calculate it. With respect to t from 1 to 3, and we enter. It's taking a minute, but should give us the answer pretty soon. Okay, so the total distance traveled by the particle from time 1 to time 3 is basically 1.96. Since this is 9, we run it up to 1. And yeah, whenever it asks for total distance traveled, that's basically an arc length problem. So you will figure out, just remember this equation from the integral from lower bound to upper bound, and square root dx dt square plus dy dt square. And okay, let's look at the last problem. The last problem, we have the tangent line equation at time equals 3. So okay, what we want to know here is we use the equation y minus at time equals 3, therefore y3 equal dy dx times x minus x3. Okie doke. So basically we know the x3 and the y3 product from the previous problem, which we already figured out at part A of this problem. So now we really want to know what's dy dx. So basically dy dx is equal to dy dt divided by dx dt. In order to help you to see this easily, dy dt divided by dx dt, that will be equal to dy dt times dt dx. So we cancel out the dt from both sides. We move the dx below, so that will be dy dt. in this case, if we want to know the dy dx at time equals 3, we basically use what we have from the previous problem. We know what's dx dt at time equals 3 and dy dt at time equals 3. So we want to use dy dt at time equals 3, which is negative 0.146, negative 0.146 over dx dt at time equals 3, which is 0.775. Okay, perfecto. Now let's plug this into our calculator. Negative 0.146 divided by negative 0.775, that's equal to negative 0.188. We don't need to round up because the following digit is a 3. And okay. So this is basically the slope of the tangent line. Since we have the slope of the tangent line, the rest is basically plug-in numbers. Y minus y3, which is 4.281, equal the slope of the tangent line, negative 0.188 times x minus x3, which we know is 3.394. Okie doke. So this is basically our tangent line equation. And typically on a test, if you left it this way, the test grader should be satisfied. But you can also take a step further to write it into y equal negative 1.188 times x minus 3.394 plus 4.281. It doesn't really matter which one you take. And that's basically all about parametrics. And thank you for watching.